I wanted to talk briefly about non-standard cells. So we're talking electrochemistry, we're talking about galvanic cells, and we know how to deal with, figuring out the voltage of a standard cell where everything is 1 molar and any gases are at 1 atmosphere. But what happens if things are not at 1 molar? Okay, then how do we deal with that? And to really deal with that, we want to talk about a couple of different concepts that we've seen in different places. Well, certainly the E0, that's going to be part of it, the voltage of that cell or the electromotive force. But we also want to talk about the KEQ and the Q, which we saw back when we were doing about equilibrium. So let's look at this. 3 different chapters have ideas about how much a reaction is going to go. In our textbook, it talks about, how product favored a reaction is. We also talk about how spontaneous things are. But in general, if we have a reaction that is definitely going to go, these 3 values show up from different chapters. And for equilibrium, we found out if we have a K that is greater than 1, especially a lot greater than 1, then that is going to be a reaction that definitely goes forward. We get lots of products. For thermodynamics, we learned that if delta G is less than 0, or if we say delta G is a negative value, then that is a reaction that is going to be thermodynamically favorable. It's definitely going to go, may not go quickly, but it's definitely going to go. So delta G, I left off the G, being less than 0. The other thing is for electrochemistry, we've learned that if you have a cell and it comes out to have a positive voltage, so we could say if the E of the cell is greater than 0, or we say that's a positive number. So positive E0, negative delta G, K that's greater than 1, all 3 of those kind of go together. Now, in the AP exam, okay, there are going to be these equations, and they're just, on there for you, and there are some definitions and there are some values of R and things given to you. But these 3 things are very useful because it connects these 3 ideas. So here's delta G, and a lot of times we do delta G equal delta H minus T delta S, but right now we're talking about delta G, and here's our KEQ, and here's our E0 value. And the idea is if I know KEQ, I can calculate delta G. If I know my voltage of a cell, then I can calculate delta G, and vice versa. And the other thing is that if I know K, then I can also figure out my E0 and vice versa. So these will connect these, and these are there for you on the exams. All you have to do is mush them around a little bit and plug and chug. So let's go back to our standard cell here, the one we've been playing with quite a bit. And this is a zinc copper. It's called a Daniell cell. And so, if we look up its reduction potentials, we're going to find out copper, okay, has this reduction potential positive 0.34. Zinc is negative 0.76. Okay, so of those 2, we say, okay, we know that the copper cell is going to be reduced more, more likely it reduced than the zinc. So we know at the copper side, the reaction that's going to occur is copper 2 plus is going to pick up 2 electrons, and it's going to become copper metal. And this is reduction. So we know that this side here is the cathode. And this is all true, but it's not really part of this discussion. Okay, in the same way, this reaction is going to happen in reverse, okay, because they can't both be reduced. So it's going to be oxidized. And the electrode where that happens is called the anode. And the reaction is actually going to be zinc metal turns into zinc ions plus 2 electrons. Well, the reason we're looking at that are 2 things. One, we want to get the voltage of the cell, and I want the equation for the cell. So let's look up here. I've rewritten the second equation, turned it around, because that's what's going to happen. And when I turned it around, it's now not the reduction potential, now it's the oxidation potential, and the sign has changed. So I flipped it around, changed the label, changed the sign. And when I put this together, we can see that the 2 electrons cancel out. So our overall reaction is going to be copper 2 plus ions, okay, plus zinc metal is going to turn into copper metal plus zinc 2 plus ions. Okay, and we can add the reduction potential, the oxidation potential, we'll get the voltage of the cell. I want to point out that we have just canceled out 2 moles of electrons. So we're going to say later 2 is the value for N, 2 moles of electrons per mole of reaction as it occurs. and we're going to need that number. So what is the equilibrium constant? We said we should be able to go back and forth and find the equilibrium constant. So what I'm going to do is take these two values here, and we can see that, here has equilibrium and here has voltage of the cell, and I'm just going to set them equal to each other. So negative RT ln of K is equal to negative NFE. So if they're both negative, we can make that positive. Divide both sides by RT. So the RTs are going to cancel out. So I have ln of K is equal to negative is equal to NFE over RT. And so I just rewrote it here. And then the last step, in order to kind of get rid of that ln, we're going to take the E of both sides. So the equilibrium constant is equal to E to this whole expression, NFE over RT. And we can get that just from these equations that are given on the AP exam. Now we want to go back now and say, well, okay, what's really going on with this situation with our copper zinc cell? Okay, so I'm going to substitute in our values. So we said that N, was the number of moles of electrons, that's 2. Okay, F, that's a constant given on there. It's 96,485 coulombs per mole of electrons. And the voltage of our cell was 1.10 volts, which we see also volt is a joule per coulomb. Okay, on the bottom of our little expression here, we have R, and this is a special R. This is 8.314 joules per mole Kelvin, and the temperature in Kelvin, 298. So looking over here on the side, I did all the units for these, and we can see what happens is, 2 was moles of electrons per mole of reaction, coulombs per mole, so moles of electrons cancel out. Volt is a joule per coulomb, so the coulombs cancel out. We can see on the bottom that the temperature in Kelvin is going to cancel out. We have joules on the top, joules on the bottom, numerator, denominator, they cancel out. And moles of reaction cancel out. So everything cancels out, which is okay because we know that K, equilibrium constant, is a unitless number. So when I do all of this expression, I get 85.675, and take E to that, I get 1.6 times 10 to the 37. Now, if a question came up, which it probably will, and it says, okay, here is a electrochemical cell, figure out the voltage, and once you have the voltage, okay, and you know the voltage and you know how many electrons are being transferred, then calculate the value of the equilibrium constant. We just did that. But what I really care about is the fact that this is a big number, 1.6 times 10 to the 37. And some of the different examples we've gotten 10 to the 91, or some huge, huge, huge numbers. So this is very, very, very product favored, which means as the cell goes, okay, it doesn't become a dead cell. It doesn't reach equilibrium until almost all of your products have, been formed from the reactants. All the reactants have turned into products, so that almost everything is used up, and that's when you finally get a dead battery equilibrium. So what's that going to do for us? The big idea is that if we take a number line, okay, and just say that it goes on and on and on all the way to infinity, that the equilibrium constant is way over here. Okay, so for an electrochemical cell with a nice positive voltage, what we're talking about, then it's got a usually pretty large KEQ way over in the right. Now, the other thing we learned about KEQs was this idea about Q, and we say, well, where are we with respect to our KEQ? Well, one Q that we do all the time, and that is the standard Q, the Q that what we'd have at standard conditions, and I'm going to call that Q0. And what that was when, products over reactants, and we're going to, in this case, use copper over zinc, and the solids don't show up in this expression. And everything is 1 molar, so Q is going to be 1. And that is always going to be the true. So whenever I'm talking about Q at standard conditions, okay, its value is going to be 1. Now in our cell, this is 10 to the 37. So the key piece here now is, well, if I have a non-standard cell, then where am I going to be on my expression? If I'm over here somewhere, okay, then that means that I am closer to KEQ, and my voltage is going to get less and less and less and less. And if I'm over here somewhere, I'm farther from the KEQ, and my voltage is going to be greater and greater and greater. So my E0 value, when I'm at standard conditions, they said 1.10 volts. So if I end up with a Q that's closer, if I just let my reaction go, then some of my reactants are going to turn into products, and I can see what's going to happen is my numerator is going to get larger, my denominator is going to get smaller, and I'm going to get a larger and larger value, and I'll end up over here somewhere, okay, closer to equilibrium. In fact, if I let it go long enough, I'll reach equilibrium. And as I go along, my voltage here is going to be less and less and less than positive 1.10 volts. And the same way, if I started with a situation where I had more of my reactants and less of my products, if my Q turns out to be smaller than 1, then I know that I'm even farther from equilibrium, and I will get a voltage greater than 1.10. So when we get a problem that says maybe, that I have a 2 molar solution of zinc, and let's say I have a 0.1 molar solution of copper ions, okay, what's going to happen to my voltage? Well, then all I have to do is figure out my Q, okay, and so in this case it would be 0.1 over 2, which is going to be 0.05. So 0.05, I'm over here somewhere, okay, less than 1, so therefore I'm farther from equilibrium. I'm going to have a voltage that's greater than 1.10 volts. Now, if I actually want to calculate that, then I would use the Nernst equation. And, okay, I'm trying to do this from memory now. Nernst equation is the cell voltage, the non-standard cell voltage is equal to the cell voltage, okay, minus RT over NF natural log of Q. And if my natural log of, Q, if I have a standard cell, Q is 1. If Q is 1, ln of Q is 0. This whole expression here becomes 0. So my voltage is my standard voltage. So if I have a standard cell, I get standard voltage. That makes sense. But if Q is less than 1, then this becomes negative. And if this part here is negative, I have minus a negative number. That's positive. And I'm going to make my voltage a little bit larger, as we said. And if Q is greater than 1, then this little thing here is going to become positive. So I'm going to subtract a voltage over here. So on this side of the Q, if Q is getting larger and larger and larger, then I'm going to get a voltage that is a little bit smaller than our standard voltage. Okay, so there is an expression here called the Nernst equation, which is no longer on the AP exam. Okay, because they're really not concerned with plugging and chugging into this expression. What the people really want you to understand, and what's really important to understand, is this big idea here, and that is that for a standard cell, the KEQ is going to be pretty large. Okay, that's the first thing. For a standard cell where everything, where all the concentrations are 1, then the Q is going to come out to be 1. And then anything that we do that increases that voltage, like let the cell run, that is going to decrease the voltage. Anything that, that lets the voltage run, Q is going to get greater and greater and greater, voltage gets less. Anything that happens that makes us farther from the KEQ value, we're going to get a greater voltage because we have a greater driving force. And that's the big idea for non-standard cells.